Hi, welcome to another video on analog electronics. So in this video we'll see the differential amplifiers, both the resistive and active loads. Let us go through this few initial slides. You should be knowing Kirchhoff voltage law, Kirchhoff current law, basics of MOSFET, AC small signal model, CS and CG amplifiers for understanding this video. Of course, you need to have a notebook, have colored pens, and you have to switch off your distractions. You need to set aside at least minimum half an hour to 1 hour uh, exclusive time for this, and write down each and everything what is being discussed here. Okay, if you are ready, we will start. So now let me just in the previous video we have discussed differential amplifier with common mode gain. So we have discussed both the single-ended gain as well as the differential gain for a differential input. So now we'll proceed with same differential amplifier resistive load, but the input is a common mode input. So when I say common mode input, V in 1 is equal to V in 2. So we'll be applying similar input to both of them. So what I'll do is I will apply an input voltage which I'll call it as VCM, common mode voltage, to V in 1 as well as to V in 2. So what I'll do is I'll take this pin and then connect it to this also here. So this is the same input is going to both this V in 1 and V in 2. So now let us try to understand how does this going to work. So now we will write its first AC equivalent. So for which I will make this VDD as AC ground. So this let me write it as VCM here, and let me write this also as VCM. Instead of writing a lengthy wire there, let me write it as on. So this is M1, M2. Let me ground it. So let me have this common source, and of course this current source will be replaced by open circuit, and this is your ground. This is RSS, and this is RD. This is V01, V02. Now since you have an input voltage of VCM to both of them, if you are assuming a current, a transconductance of GM for this as well as for this also GM, so I can find out what is the current that is flowing here. So the current that is flowing here is because you can see whatever current that flows will be in this direction. The same current is flowing in this direction, and this current ID, if you cite ID1 is equal to ID2. So this is what is ID2 here. So this is ID1 is equal to ID2 is equal to VCM into GM. So transconductance times the input voltage is the current. If you see both the currents are flowing in the same direction, ID1 and ID2, so both of them are coming here, and then they have to pass through this RSS to go to ground. So now for further analysis, what I'll do is I'll just split this vertically apart half. So when I'm just splitting this half, so this RSS is common for both M1 transistor as well as M2 transistors. What I'll do is I'll split this resistor RSS into two resistors of value 2 RSS. So this is now 2 RSS and this is again 2 RSS. Now the circuit now reduces to something like this. So this is my circuit now. So this is PCM, this is grounded, and this is again now grounded here. This is 2 RSS, and this is so and so, and this is V01. You have a current of ID1 flowing here. This is RD, and this is like okay M1. How about this? So this is also having similar type of configuration. This is 2 RSS. This is now VCM. This is again AC ground. This is RD. This current is ID2. ID2. This is V0. So now if you carefully look at this, so this is also NMOS transistor, this is also NMOS. You have at the source 2 RSS connected, at the source 2 RSS connected. So are these two identical? So these two are identical and they are like CS amplifier with source degeneration. CS amplifier with source degeneration. So we know that CS amplifier with a source degeneration will have a gain, so which is nothing but V01 by VCM is equal to minus of GM into okay RD divided by 1 plus GM into 2 RSS. So this is the expression for gain of a CS amplifier with a source degeneration. This is V01 by VCM, which is also equal to V02 because V01 and V02 are identically same. Whatever gain that I have for V01 by VCM will be the same for V02 by VCM also. So shall I say this as this is a gain of an amplifier with common mode input but measured single-ended. So this is ACM SE. ACM SE is nothing but the gain of the differential amplifier with common mode input. CM stands for common mode. So when I say this ACM SE, so what is this? This is nothing but voltage gain with common mode input with single ended measured output. The output is measured single endedly, whereas the input is applied commonly. So both the inputs, both the terminals are getting same input. And in such case, in this case of common mode, this is not a virtual ground. This is not a virtual ground. So in case of differential input, we were getting this as 0 voltage, so that was a virtual ground. But here this is not a virtual ground. So virtual ground concept will not appear, will not exist when you are applying a common mode signal. What I mean by common mode is both input 1 and input 2 are getting the same signal. So that can be analyzed by rewriting writing its AC equivalent circuit and then rewriting this as so and so. This will become a CS amplifier with source degeneration with resistance source degeneration resistors as 2 axis. So of course we can also find what is common mode gain when you're measuring it differentially, which is nothing but V02 minus V01 by VCM. If you can see, since V01 by VCM and V02 by VCM is same value, the subtraction of that will actually become 0. Meaning of this is, if you are differentially measuring the output voltage by applying a common input, you will actually get 0 output voltage because they're going to cancel out. So that's what is this ACMD stands for. So what is this? ACMD is, it's a gain of an amplifier with common mode input but differentially measured output. So now once we know what is, let me just recap what is the differential and common mode and the single-ended things. I hope okay these are the things what we have. So let me just rewrite it here. So this is DSE which is V01 by VID. It is equal to minus GM RD by 2. Another ADSE which is V02 by VID. So this is pertaining to the last video. GMRD by 2 ADD, that is differentially measured, voltage gain with differential input but differentially measured, which is nothing but V02 minus V01 by VID will be equal to GM into RD. There is one more possibility. You can write it as V01 minus V02 by VID. In such case, this will become minus GM into RD. Minus GM into RD. This is for a differential input. For a common mode input, which we can write it as VCM single ended. It is now GM, of course, minus GM RD divided by 1 plus GM into 2 RSS. So this is same for V01 by VCM. Even if you write V02 by VCM, V02 by VCM, you will have the same expression. So it is minus GM RD by 1 plus GM into 2 RSS. This is also ACM AC. So then what is ACM differentially measured? So it is commonly applied but differentially measured. So this is ACM D. So now can I write it as this is nothing but V02 minus V01 by VCM, that's equal to 0. Even if you write V01 minus VCM, V02 by VCM, here also it is the 0. Here also it is 0. So once we have these common and differential modes, we will define one more important parameter, which is known as common mode rejection ratio. Common mode rejection ratio. So this common mode rejection ratio is nothing but AD by ACM. So depending on whether you are measuring single ended or differential, you can write it as ADSC by ACM AC, ADD by ACM D. This is common mode rejection ratio single ended, common mode rejection ratio differential. So this ADSE is nothing but you have GMRD by 2. Simply take the magnitude, and this is take the magnitude of this. You can neglect this one from this. So is it not GMRD divided by GM into 2 RSS. So this GMRD will go with this. This 2 will go with this. So you'll end up with GM into RSS. This is what is CMRR AC. So now this is actually GMRD. This is actually 0 because ACMD. You can see ACMD is 0. So this happens to be infinite. So this is how you can able to find out or get an expression for CMRR, which is single ended measured and differentially measured CMRR. So this is the best CMRR you can ever think of. This is the ideal CMRR. So that's about the differential mode amplifiers with resistive load. So as we already know that these will have a limited gain, and in order to get better gain, we'll go for active load differential amplifiers. So we will do the same thing now. So let me show you differential mode, active load. Just give me a minute. So this, I didn't open that. So let me just open this quickly. So now okay, sorry, I didn't keep it open. It's wasting your 2 minutes of time. Sorry for that. So what we'll now see is, I will not write, but I will just show you the circuit diagram which is there in the textbook and try to explain so how it happens in a differential amplifier with active load. So when we actually have an active load, maybe let me just write the circuit diagram once for you people so that you can have a practice of that differential amplifier with active load. So this is how it starts. So this is VDD here. This is how it goes. This is PMOS, this is also PMOS, this is NMOS, this is NMOS. These are two inputs. The output is measured here. Now of course you'll have a current source here. This is minus VSS. You can think of having a source, current resistance of so and so. This you can name it as M1, M2, M3, M4. So of course in this active load analysis, lambda has to be non-zero. This is V in 1, this is V in 2. So with these specifications, why it's taking so much time? So now, okay, this is the differential amplifier what I have. These are all the material which is there in the textbook. I'm just borrowing the circuit diagram from the textbook. So what it says is, so maybe let me just zoom it up. So now this is the exact circuit. Instead of writing M1, M2, it is written as Q1, Q2, Q3, Q4. You can see this is VDD, this is minus VSS. So this is there are two single-ended inputs. So this is VG1, VG2, and here you have your output voltage. Suppose if you consider the DC current analysis, this is the DC current what you are having at the tail. That is both sources shorted and connected to this. And if you can carefully see, since this is actually Q1, Q2 are perfectly matched. Now whatever current I you have, so each transistor Q1 and Q2, which is M1 and M2, will take half of the current. That's why this current is I by 2, this current is I by 2. And you can see this is basically looks like a current mirror. So since the dimension of Q3 and Q4 are identical, then whatever current that is flowing here will go on to mirror it here. So this is the current that is flowing due to this current mirror. If you write a KCL over here to this node, so this is the current I by 2 entering, this is the current I by 2 leaving, and no DC current goes to the output. No DC current goes to the output. So that's what is. So no DC current at the output is the conclusion of this. Of course, it has got two differential input and it has got one single end output. So now we'll just move on to. Now, if you can see here, even though the current, the DC current that was going out from your active load differential amplifier was 0, but if you carefully look at what is the current that will go out of the output terminal when you're applying a differential input. You can see now this is a differential input VID by 2. This is minus VID by 2. So as you know that if you are applying two inputs of same magnitude but out of phase, it's like a differentially applied but balanced input. So this is a differential balanced input, and this is 0 because we have zero current flowing through this resistor here. Of course you can think of a resistor here, so maybe I can just show it here. Since you have this as VID by 2, this is minus vid by 2. The id1 will flow here, and the same quantity of id will going to flow here. Let me just take out this id. Since the same current flows from M1 and M2, actually zero current flows to this. When it is zero current, for AC analysis you ground it, for AC analysis you ground this. So when zero is the current flowing through this RSS, so then this looks like a zero. This looks like zero. So now that's why this is written as 0 here. This is written as 0. So 0 actually stands for the virtual ground. 0 actually stands for the virtual ground. So more importantly, what to understand here is whatever current that you have here, this is I, the same current is going back here as I. Whatever current you have I here will be mirrored here as I. You can see now you have two currents flowing in the opposite direction. If you can think of the current that may go out of the output terminal will be 2I. So this is what is one of the biggest advantage of having this current mirror as an active load for differential current differential active load amplifier. And let us try to understand how do we find the gain of this type of amplifiers. Gain of these type of amplifiers will not be found as we found it for CS and CG and CD amplifiers. We just follow a different topology. The topology that what we follow is we just find the value of AV, which is nothing but GM into R out. So what is this GM? GM is nothing but short circuited transconductance. You make your output voltage grounded. Try to find out what is IX and VX. IX and of course when I say VX, it is the input voltage that you have applied. So GM is nothing but, of course, if you are naming it as I naught, so it is like I naught by VID. I naught by VID. So that's what is shown here. If you can just go here, see, sorry, I had to write the current direction this way. You can see now. This is your small signal model of. Let me just go back here and so this is what we're looking at. So here this is differential amplifier with active load. You can see this is AC grounded, this is virtual ground. I applied plus VID by 2, this is minus VID by 2, and the output is grounded because you're supposed to find capital GM, which is nothing but I naught by VID. This is I naught, which is current going out here. VID is the input voltage that you applied. So to find this, let us try to find an expression for I naught. To find the value of I naught, so we are trying to write the KCL at node A. Suppose if this is what is node A here. This is what is node A. Of course, you can see why this is written as so and so. From this to this, why it is written so. If you just look towards the drain of this M3. So since this drain and gate are shorted, the resistance looking up is 1 over GM3 parallel with R0. That's what is written here. As drain and gate of Q3 are shorted, the resistance looking up is 1 over GM3 parallel R0. That's what is written here. So this entire circuit is now replaced by a simple resistor whose value is 1 over GM3 parallel with R03. And this is the voltage VG3 that will be applied to gate of M4 or this Q4. So now you have this transistor can be rewritten as its AC equivalent can be written as this. So which will going to have a current of GM4 into VG3. Suppose if I just zoom it out, this is actually GM4 into VG3, and this is the current what you are having. So we are writing a KCL here, which is nothing but KCL at node A is I naught. This is I naught which is going out. Another current is this current this current is actually zero. Why this current is zero means because this is grounded, this is also grounded, that's why it is zero, and this current is also zero, and this is the one current which is leaving, so which is I naught. The other current leaving is gm4 into vg3. That's what is written here. So these two are the currents which are leaving. The current that is entering is this. The current that is entering this node is gm4 vid by 2. gm2 into vid by 2. So this is what is the current that is entering this node A. So upon rearranging, of course, this has been already discussed in detail in another video. You can see the transconductance comes out to be small gm. So this is actually the algebraic sum of this gm of this and gm of this, which is of course it is gm2 by gm2, which happens to be gm. So once you know what is capital Gm, so as we know that we are supposed to find the AV of the amplifier, which requires Gm and Rout. We could able to find what is Gm, which is nothing but the transconductance of either of these two, because these two are identical. Next we need to find what is Rout is. So to find Rout, so as we know that we have to ground the inputs. So that's what is, this is Rout of a differential amplifier. This is grounded here. You can see this is grounded. Now you are applying a dummy voltage source Vx, you are trying to find what is Ix. So of course, maybe you can just refer to the old videos where I have clearly explained what is the derivation for this Rout. So Rout actually comes out to be R04 in pair with R02, R04 in pair with R02. So this is what is the Rout. So once you know GM and Rout, that's what is written here. Once you know what is Gm and Rout, you can easily find out what is gain of the amplifier. So gain of the amplifier becomes small gm into R02 pair with R04. Next, of course, you have to find what is the common mode gain. For common mode gain, as you can see here, this is same input is given to both of them. You can see now this is same thing here. Now this RSS has been split onto either side as 2 RSS, 2 RSS. And they are trying to find what is the current flowing through them, and this is what is the current that is flowing through this. So that's what is given as VICM by 2 RSS, because this acts like a this is having almost the same voltage as your VICM, so that's why it is in your source degeneration. If this resistance is too large, so whatever voltage that you have at the input, same voltage will be appearing here, of course, which is discussed in detail in the other videos. So when you actually have a look at this overall expression, so this ACM comes out to be minus of 1 over 2 RSS into GM3. So once you have the expression for common mode gain and also for the differential gain, we can find what is CMRR. So upon finding the CMRR magnitude, which is nothing but AD by AC, this happens to be GM into R0 multiplied by GM into RSS, which will be a very huge value, because GMs will be, of course, GMs will be maybe in terms of millisiemens, whereas R0 and 2RS, R0 and RSS will be in terms of hundreds of K. So that's why you're going to have a very good CMRR for a single-ended measured differential amplifier with active load. So this way, of course, this requires bit understanding. I'm not repeating the things what I already told in the previous video. So just log into that previous video. Just listen to me exactly what I did. Okay, what are these current equations, all those things. You can easily understand what we're talking about and how do you get these expressions for different parameters of GM, Rout, and common mode gain. So this is about the differential amplifier, resistive load and active load. Thank you.